Hello, everyone. My name is John Holt, and I'm your host for today's episode of Eyes on Earth, a podcast of the U.S. Geological Survey's Earth Resources Observation and Science Center. Today, we're talking about the past and future of Earth observation. A movie camera attached to a captured German V-2 rocket got the first images of the Earth from space in 1946, but it took another 13 years to get imagery from an orbital satellite, and 13 more after that to launch the first Landsat. For years, Landsat was the only game in Earth observation. Other government space agencies launched satellites slowly, with years passing between each launch. Fast forward to the present day, and the game has changed dramatically. More than 1,000 satellites were launched between 2012 and 2017. 335 launched in 2017 alone. How do we keep track of all these birds? And more importantly, how do we keep track of how good they are, what they're good for, and how they might work together to monitor the Earth's surface in the interest of science? Our guest today wrote a guide designed to answer questions like that, or as we call them in the USGS, a circular. His name is John Christopherson. John, welcome to Eyes on Earth.
Thank you.
So let's start by having you tell us a little bit about what you do here at EROS and how you got into the game of Earth observation.
One, I've got plenty of gray hair, so I've had a rather long career. I've been involved with electro-optical imaging since I got out of college, my first job. Originally doing it for defense work, and then shifting the company I was working for in California, made all of the sensors for the first 7 Landsat satellites. And I got involved with creating or helping to build the Enhanced Thematic Mapper Plus for Landsat 7. I came out here originally to help work with the quality assurance efforts, the calibration efforts for Landsat 7.
Can you give me just a sense of what you mean when you say calibration? What are we talking about doing to make them the best calibrated, and what does that mean?
Calibration is just a way of ensuring that it is of the highest quality. I like to say that Landsat and other satellites don't take images of the Earth, they take measurements of the Earth. So the two big ones are geometric and radiometric accuracy. Are those pixels precisely where they should be? And are they reporting back what they are measuring?
World of difference from a movie camera on a rocket.
Yes. Yeah.
So
but you got to start somewhere.
Right. You know? Yes, that's right. You have to start somewhere. So let's talk a little bit about how Earth observation has evolved from a movie camera on a rocket to the point where you're at today, talking about calibration of the radiometry and geometry. How many Earth observation satellites are up right now? Do you have that on the tip of your tongue?
It's varying day by day. The Union of Concerned Scientists keeps a nice operational catalog of satellites in the air right now, and they're tracking over 2,000 operational satellites, of which 750 to 800 are operational Earth observing satellites.
But when we started though, when Landsat started, it was one? There was just a handful of satellites?
There was one plus the military.
But in terms of the satellites that were up, that we knew about, that civilians had access to.
Civilian satellites? Civilian remote sensing, if you look at Earth observation, actually started much earlier with the first weather birds. But for land imaging, which is near and dear to EROS's heart, Landsat was truly the first civilian dedicated land remote sensing satellite to serve land science.
Right, where we're not looking for weather, we're not looking at clouds, we're looking at what's happening on the ground.
Right, weather and clouds get in our way.
We are not quite as big a fans of those.
Right.
So we started with Landsat, and I think I mentioned in the intro, it used to be years, right, between the launch of an Earth observation satellite.
It was Landsat and Spot, the two main things, until the late 90s.
And then we pass 1999, 2000, and a few more Earth observation satellites come online, and something called JC appears. Is that right?
Yes.
Is this
yes.
JC? Is it one of Frank Zappa's kids? I mean, what is a JC? What's that?
Well, some interesting things happened in the late 90s. First, the planning for the mission to Planet Earth, which is a effort to get multiple satellites with multiple instruments measuring broad Earth conditions to get a more holistic picture of what's happening on our Earth. That was an exciting time. But then also In late 99, early 2000, we saw the launch of the first commercial high-resolution satellites. IKONOS offered 1 meter resolution imagery, which was astounding to us at the time. The Digital Globe Corporation launched the first QuickBirds, other satellites, and there were questions about, well, are these data any good? And so JACIE was formed. JACIE stands for, it's JACIE, the Joint Agency Commercial Imagery Evaluation.
It's quite the mouthful.
Effort. Yes, that's why we say JACIE.
So this group came together to answer these questions about just a couple of commercial satellites. So at that point, we had Landsat, we had Spot. There were a few other sort of civilian government satellites out there. These commercial players come in, but we're still talking about a pretty low number of actual systems that are collecting imagery over the Earth.
Right. Of the systems we could get our hands on data from, you could still count them on 2 hands, even up through most of the first decade of this century.
So in 2000, you're talking to these people, and you can still, like you say, use your hands to count the number of satellites. Last year, there was a JACIE conference, right? There's a JACIE gathering and get together
This is
every year.
An annual. Mm-hmm.
How many satellites were you talking about, or could you have potentially been talking about last year at your JACIE conference?
Oh, potentially we could have been talking about hundreds, but in actuality, we did report on, I'd have to go back and look at last year's agenda, see what we report on, but probably a dozen or less. There were the Landsats, Sentinels. The Europeans now have, it follows on almost in spirit to the original mission to Planet Earth, Earth Observing System. They now have their Copernicus system. And then we also had commercial players there from Digital Globe. Is still very active in this. Over 50 countries have land observing satellites.
Wow, it's a big leap, a big jump from where we were even 20 years ago. So I suppose that brings us to the book. Tell us about the book. Why a compendium? What makes this product useful and unique for land imaging satellites?
There are a number of resources out on the web where you can find out different satellite characteristics, but they all have certain limitations to them. One, the CEOS, the Committee on Earth Observing Satellites, they have a great database, but that leaves out the commercial birds. There is a site maintained by ESA, and the
ESA, you're talking about the
European Space Agency.
European
Excuse me. We live by acronyms here.
Right.
They have a lot of very, very, very detailed information, but it's hard to pour through there and just find the basics that you need. And again, they're missing a few satellites. Union of Concerned Scientists has their database, but they don't have the technical details, remote sensing details that we like to have in there. So we decided to put together a book of these.
Why are there so many satellites? How has it become such an explosive thing? Let's talk about maybe CubeSats. Is that?
Oh, and that's all part of it. Numerous factors have come together for this. First of all, dealing with Earth observing data in the last 2 decades has gotten so much easier. In the very early days of EROS, the majority of users got their data on printed pieces of film. But it was around the late 90s that finally PCs became powerful enough, desktop, laptop computers powerful enough to deal with massive amounts of data that is a Landsat scene, which now we don't think anything of. There's a confluence of technological developments that are driving this. One, the ease of computing. We can deal with this data so much easier now, so much easier than in the past. Launch vehicles have become cheaper. There are well over 100 different launch systems under development now, different systems being developed right now. Everybody and their brother's trying to build a rocket to space. Satellites can be made smaller with a lot of new technologies, advances in microelectronics and so on. You can make satellites smaller. You can put multiple satellites on one launch. Not long ago, India launched over 100 satellites in one launch. Wow, must look like popcorn coming out of there. So now you're only paying for 1/100th the cost of a rocket, and the launch is cheaper to begin with.
So you say 1/100th of the cost of a rocket. I think, again, we're talking about CubeSats, which are loaf of bread size or larger kind of satellites.
On that launch vehicle that launched over 100, some of them were CubeSats, quite a few of them were. Some were small sats. There's different classes. CubeSat is a buzzword that is bandied around right now,
right.
basically what we're talking about is satellites weighing anything from a few pounds to a couple thousand pounds.
Which again allows you to put a whole bunch of them on one rocket.
Exactly. And now you can divide the cost of that launch among many passengers going up there. If we each had to pay for the entire jet when we flew across the country, none of us would fly. But because we're dividing that cost with a couple hundred other passengers, it's pretty affordable.
So we're literally to the point where satellites on a rocket are like passengers on a jet airplane, and that's what's making this possible. That's what's making the economics work to get so many satellites.
Right. It is. It's opened up economically access to space to far more people than ever before, particularly small companies, commercial companies. People are seeing niches that they're hoping they can fill with this.
When you say there are a lot of players, I mean, it's not just commercial. It's like you're talking about commercial is kind of the big area where we're seeing the growth. But colleges, I feel like I've read stories about high school students putting together satellites and hitching a ride on these things.
If you've got $5,000, you can buy all the parts to build your own satellite. One of these little CubeSats, which, by the way, a CubeSat means that it's 10 centimeters by 10 centimeters by 10 centimeters, about 4 inches on a side, a little box. And yeah, that costs about $4,000 or $5,000. You can buy it online with a credit card and assemble it yourself, and then you've got to go find a launch vehicle. But NASA is very generous with education support and so on. You can catch a ride up to the space station. The space station has ejectors that can eject satellites from it into a fairly low Earth orbit. They don't last too long up there, but you can live for a year or two.
So how do you go about getting approval? Like if you're a high school teacher and your class builds a satellite, can you just call NASA and say hello, and then they give you a form or something? I mean, how do you do you need permission to do that?
Yes. It's a fairly long and harrowing series of regulatory hoops you have to jump through. Within the United States, it's governed by the Department of Commerce, permission to launch and so on. The FCC also weighs in on that. They ask, we've got people at the USGS headquarters who sit on the board to approve these launch license applications.
So it's not quite as simple as calling up a rocket like an Uber. There are several steps that need to happen.
Yeah, we don't have Uber for space yet. So, but yeah, you've got to make sure that there are some rules for operating up there. You must deorbit. You must have certain capabilities to be safe. One of the reasons CubeSats are 10 centimeter by 10 centimeter and not smaller, we can make satellites even smaller. But that gets difficult to detect on radar. And they want to be able to track all of these things up in space so that you can avoid collisions, intersections, and so on. And so, yes, they just made that arbitrary limit 10 centimeters. And by golly, everybody's building CubeSats. This is the most exciting time. Things like the cloud bringing computing power, unimaginable amounts of computing power to bear on this, access to data, measurements of the Earth being taken at higher frequencies and greater densities than ever before. Science that is going to be possible with all of these data is mind-boggling.
But again, it's got to be good, it's got to be trustworthy, and it's got to be able to work together. John Christopherson, thanks for talking with us about the past, present, and future of Earth observation. It's been fascinating. We hope that you come back for the next episode of Eyes on Earth. This podcast is a product of the U.S. Geological Survey, Department of Interior. Thanks for joining us.